Good morning. At first, I remind you some parts of the topics that we had yesterday. You remember we started with the G, which was S of F and N. M was not equal N, and N was greater than or equal to. And then we formed G hat, which was G tensor product over F of F C plus minus 1 divided from FC divided from FP. Then we suppose that P hat is a partition of R hat. R hat was the set of, in fact, G hat was direct from G hat gamma, where gamma is an element of R hat, and R hat is the subport of in fact, G hat has a data space decomposition with respect to H. H was H direct sum FC direct sum FB. And P hat, we thought P hat to be a parabolic partition of R hat. And then we form G hat plus, which was G hat gamma, where gamma is an element of P hat minus 0, and then we put B to be H direct sum G hat plus. We start with a lambda belonging to H star, and then we got the representation of H corresponding to this lambda, and then we consider FB as a module over B by the action of this part as 0, and then we make this tensor product over UB, and then we call it M, and we show that M is S panel FI1 R1 FIT RT B. You remember I told you that instead of one tensor B, I just write B. So M is S panel FI1 R1 FIT RT B, and here R1 I1 is less than IT. T is a positive or positive integer or 0. R1 up to RT are greater than 0 or equal 0. And if Fij is of degree 1, J is 0 or 1. And you remember we fixed some elements, each Fi is an element of G hat minus alpha I. And then we show that M is direct sum of M mu. We go back to H star. We prove that M has a weighted space decomposition with respect to this H. Where is H? M is a UG hat module, so it is a G hat module. H is a subalgebra of G hat. So we can consider M as an H module, and as an H module, M has a weighted space decomposition like this. And we prove that Fi1 R1 F ITRTB is an element of F lambda minus R1 alpha 1 alpha R1 alpha I1 minus RT alpha IT. Especially if we look at this, it is a subset of M. Yeah, it is. Okay, and if we want to form M lambda is exactly FB, right? Because we don't have this part. So M lambda is just FB, right? And now we want to prove that if K is a submodule, proper submodule of M, then K lambda is if K is a submodule of M, then K lambda is 0. And you know what is K lambda? K lambda, you remember that if M has a weighted space decomposition, I proved this for you maybe in the second lecture. I cannot remember exactly which lecture, but maybe in the second lecture, I proved that if M has a weighted space decomposition with respect to a Lie algebra, each submodule has a weighted space decomposition. Yes? And if K is a submodule of M, then K lambda is K intersection M lambda is exactly 0, and you can see why this happened, because if K intersection M lambda is not 0, we get that, I told you M lambda is just FB. We get that V is an element of K. And as K is a submodule, we get that Fi1 R1, Fit RT, V is an element of K for all indices like this, right? Because it is a submodule, and a submodule must preserve the module action. So this is an element of K for all indices like this. But we know that M is exactly a span of these elements. So it means that K equals M. And it is a contradiction because K is a proper submodule of M. Okay? And so what was the problem? The problem was started from here, that I assume that K intersection M lambda is not 0. This gives that K intersection M lambda is 0, and then K lambda, which is K intersection M lambda is 0. In fact, V is not an element of K. And we have another lemma. There exists a unique maximal submodule of M, I will call it M, such that B is not an element of M. We want to prove there exists a unique maximal submodule N of M such that B is not an element of M. Okay. Set N to be the summation of all K when K is a submodule of M and V is not an element of V, of K. Okay. We get N to be the summation of all submodules of M which does not contain this V. Okay. And each submodule K of M you know that each submodule of M inherits the vector space decomposition. Okay. It's better to write here proper because I'm working just with proper ones. It's clear when V is not an element of K, I can put this here because V is not an element of K, so K is a proper submodule of V. Each proper submodule K of M has a vector space decomposition with respect to H. In fact, K is summation of K lambda. Lambda is an element of H star with K lambda K mu mu. K mu is just M mu intersection K. Okay, so N is summation of N mu when mu is an element of H star, and for each mu, N mu is just summation of K mu. Okay. And now, in particular, N lambda is summation of K lambda when K is a proper submodule of M. And then this shows that because I told you that each K lambda is 0, it implies that N lambda is 0, right? In the previous lemma, I showed that if K is a proper submodule of M, then K lambda is 0. So N lambda is a summation of K lambda. When K is a proper submodule of M, K lambda is 0, so N lambda is 0. It means that N is a proper submodule of M. we told that we want to prove there exists a unique maximal submodule of n of m such that V is not an element of n, and I get n to be the summation of all proper submodules. Proper submodules are those modules that does not contain V according to the previous lemma, and we get that n lambda is in fact n lambda is 0, and so it means that V is not an element of n, and and we prove that it is unique because I just get the summation of all submodules, and this summation is unique, right? Okay. It is exactly equivalent to submodules which are proper. The summation of all proper submodules is a module which is again proper, and as it is proper, V is not an element of n, and it is unique because it is the summation of all submodules. Okay. So we have M and we have N. N is a unique maximal submodule of M which does not contain V. N is a submodule of M, and I can form M over N, right? And you remember, I told you that submodules of a quotient is a quotient that contains n and is a submodule of n. And as n is a maximal submodule, this does not contain any non-trivial submodule. So it is an irreducible module. It is an irreducible G hat module. Okay, let's look at some properties of these modules. We saw that M is UG hat V. In other words, M is generated by V. If you have V, you have the entire M, right? Because you have V, and then using the module action, you get all the elements. We say that M is generated by V. M has a weighted space decomposition with respect to H. M lambda is precisely FV. And another thing that we have is this one, that UG hat plus V is 0. It is the way that we define the module, right? So we have this property, we have this property, and we have this property. And for M over N, I denote it by induced module from P hat. And for these modules, that for simplicity, I call it M tilde. As M is generated by V, and this is a quotient of M, so this quotient is also generated by V. Yeah, of course, by V, I mean V tilde, just for simplicity, I identify V tilde, which is V plus M just by V, and I can say that M tilde is UG hat V. We identify V with V hat. As M has a vector space decomposition, we get that N, which is a submodule, has a vector space decomposition, and then the quotient has a vector space decomposition. So M tilde also has a vector space decomposition. Especially M tilde lambda is M lambda plus N over N. And as M lambda is one-dimensional, and we know that M lambda is exactly FV, we get that M, it is FV tilde, that's with this identification, it is FV. And because UG hat plus V is 0, and the module action of the quotient is induced from the module action of M, for this quotient also we have this one. So, okay, where should I write this? So we have UG hat plus V tilde is also 0. And another property is that M tilde is irreducible. So, what is the story? You remember we had a partition parabolic partition of R hat, then we get a decomposition for G hat. Then we use a lambda belonging to H star and an irreducible module, irreducible H module, CV. Using this, we form M, and then we get induced FV P hat. And what it's saying, look at this. What was our aim? We wanted to find modules for G hat. We want to have irreducible module for G hat. And this shows us how we can get an irreducible module for G hat. It is enough to get a parabolic partition. Then you have this. Then you start with an irreducible H module. And finally, you get an irreducible G hat module. Right? It is kind of irreducible G hat module. And that I showed you exactly what we can form this, how we can construct it, right? It is something that we call it highest weight modules. We say highest weight module, it is weight module because we start with an element, and this element is a weight vector. It is an element of M lambda, so it is a weight vector. It is generated by a weight vector, and when we say highest, it means this, right? And look at this. For each element of this part, if we get one element of this part, and then for the module action of this element over this field, we get 0. If E is an element of G hat alpha, and alpha is an element of P minus 0, then E M lambda, it is easy to see that it is a subset of M lambda plus alpha, right? But this one is 0. It means that after lambda, we don't have any weight. So it is the highest one, right? It is the meaning of this highest weight module. We say highest weight module because we don't have lambda plus alpha as a weight when alpha is an element of P minus P hat minus 0. And you remember, I told you that M is direct sum of mu, and support of M was a subset of lambda minus alpha I1 minus alpha I2, like this, right? So, and it's the meaning of highest weight. When we say highest weight, it means that after lambda, in some sense, we don't have any weight, right? And it is something that I showed you just in one example. I started with SL and N, but we can do it in general for a class of the superalgebras that I will explain for you. Suppose that G is a finite dimensional simple the superalgebra. Such that you remember I told you when we have a Lie superalgebra, the even part is a Lie algebra, and the odd part is a module for the 0 part, right? G1 as a G0 module is a direct sum of irreducible modules. G is equipped with a bilinear form and let's work with C. There is no difference between C or an algebraically closed characteristic 0. I just put it to C because in the literature, the definition of this kind of the superalgebras is just the superalgebras defined over C. Because of that, I put C here. Okay, G1 as a G0 module is a direct sum of the reducible modules. G is equipped with a bilinear form satisfying G1, F was G1, G0, 0. The form is non-degenerate. Xy, F was -1 degree X degree Y, Yx. And Xy, Z, F was X, Y, Z. Here, when we write degree, it means that X and Y are homogeneous, right? So, you remember the previous example, I exactly defined a bilinear form, and that bilinear form exactly satisfies this, right? So that example is just an example of this kind of these superalgebras, because the first part also is it's not so easily to see, but it can be proved that G1 and the G0 module is a direct sum of irreducible modules. So we refer to such a Lie superalgebra, a basic classical simple Lie superalgebra. We say classical because of the first condition, and basic is the second condition. The existence of such a form guarantees that we call G basic. Okay. So, suppose that G is a finite dimensional simple Lie superalgebra over C such that 1 and 2 are satisfied. We call G a basic classical simple superalgebra. Basic classical simple Lie superalgebras are classified, and they are known as types A and N, A and N, B and N, C N, D and N, F4, G3, G2, and I wrote everything, yeah. And types of finite dimensional simple Lie algebras. Okay. Each finite dimensional simple Lie algebra is also considered as a basic classical simple Lie superalgebra. And if I want to be more precise, it's better to write here G1 is 0 or. Okay, because I told you that when we are talking about irreducible modules, I assume that that module is not 0. So I write here G1 is 0 or G1 and the G0 module is a direct sum of irreducible modules. And so any finite dimensional simple Lie algebra is also a basic classical simple Lie superalgebra, right? And you remember, I told you types of finite dimensional simple Lie algebra is A, B, C, D, E6, 7, 8, F4, G2. But that F4 and G2 is different from that one because there were as a sub 2 and 4. Okay. And now just mention that AMN, it is just SLMN that I told you. Of course, SLMN is AM minus 1 and minus 1. And because of that, I suppose that MN is greater than 2. And if M is not equal N, the structure is different from that one that I told you. You remember, I told you that M must not be equal to N, and it is because SLMN that I introduced you is not simple if M equals N. But here I want to have a simple one. So I suppose that M is not equal N, and for getting A and N, just need a quotient that I don't want to go through it. But anyway, they are classified, and these are the types of basic classical simple superalgebra. I don't want about the structure of these basic classical simple superalgebra. I just want to mention some of the properties that they have, because they have the same property. The structure is different, but they have the same properties.
Are we going to talk about the Affine superalgebras?
Yes, exactly. Because using G, that G was just SLMN, and then I could form G hat, right? And now I start with a basic classical simple superalgebra, and I get again G hat, and G hat is an affine superalgebra, right? Okay. Basic classical simple superalgebras. G0 contains an abelian algebra H, abelian, and of course finite dimensional, because G is finite dimensional. G0 and G1 have weighted space decompositions with respect to H, setting Ri to be scaffold of Gi. We get that R0 intersection R1 is empty, and 0 is an element of R0. You remember when we have a basic classical superalgebra, there is a bilinear form here. I write it with corresponding bilinear form. And we have.
Sorry, I have a question. Can you like in the classical setting, I think you can decompose like the algebras into semi-simple part and solvable part.
And which part?
Semi-simple and solvable, and semi-simple are some of.
Okay.
Is something like that true also with Lie superalgebras?
With Lie algebras, you mean?
No. Like in the classical setting, you try to classify simple Lie algebras because the sum of to give semi-simple algebras, and then we can get a general algebra by summing with solvable the algebra.
Yeah, but be careful that my superalgebra is simple.
Yes.
It is simple by itself.
But like, are all like generally superalgebras? Can you construct?
Okay. You are talking about something like Lie algebra.
Yes, yes.
That we can in Lie superalgebra we must be so careful. You know, it's not that easy as in the classical case.
Yes.
Yeah. But my Lie superalgebra is just a simple Lie algebra, so we just have that semi-simple part. I should mention that a lot of things that you know in Lie algebras are not true in the super case. For example, when you say semi-simple Lie algebras, you know what is those Lie algebras. But in the super case, it's somehow tricky because when you want to define semi-simple, what do you mean by the semi-simple? It is direct sum of simple ones, or there is no solvable, or the radical solvable is zero, and these are different in super case. Okay? Yeah. We can define them as we say, okay, a Lie superalgebra is the semi-simple if it is a direct sum of simple. Or we can say, no, I define solvable ideal and I say it is semi-simple if the solvable ideal is zero. But when we want to compare these two, these are not equivalent in the super case. Okay? Okay. Ri is support Gi. R0, R1 is empty, and 0 is an element of R0. G is equals direct sum G alpha when alpha is an element of R, and for R, I mean R0, R1. And G alpha is G0 alpha is an element of R0, and G1 alpha is an element of R1. And G0, which is G00, is H. Okay. And G alpha, G beta is 0 unless alpha plus beta is 0. In particular, the 4 over H is non-degenerate, right? Okay, and the other things, yeah. Okay. For each alpha belonging to R, which is not 0, there exists E plus minus alpha in G plus minus alpha, such that H alpha bracket up H alpha E plus minus alpha is plus minus 2 E plus minus alpha. It is another property and something else. For each alpha which is not equal to 0, dimension of G alpha is 1. These are the common properties of basic classical superalgebras. And now, as you mentioned, we can define G hat. Suppose that G is a basic classical simply superalgebras, and set G hat to be G tensor Ft plus minus 1 direct sum Fc direct sum Fb, and you are expert enough, so I don't write down the brackets. You know what is the brackets. Okay. The V brackets as before. And you can see that, I should write here C, because I suppose that my field is C now. Okay. And this is a Lie superalgebra. This Lie superalgebra is called an affine Lie superalgebra, but it is called untwisted affine Lie superalgebra. In general, affine Lie superalgebras have a meaning, have a definition, right? And according to the classification, we have two kinds of affine Lie superalgebras: twisted and untwisted. And the structure of untwisted ones are exactly the thing that I told you, according to the classification. But we have also twisted one, and the structure is very complicated. Okay, and these are untwisted affine Lie superalgebras. If you are interested in, just let me know. I will tell you some references for twisted affine Lie superalgebras as well. Okay. For simplicity, I write L for G hat, right? Okay. As in our example, L is G hat, it is G tensor CT plus minus 1 C plus CC plus CD. As before, we identify H tensor 1 with H. So I put H direct sum CC direct sum CD. And now what we have, I can write this. You remember the properties of G was that we had a decomposition for this G. It is summation G alpha, alpha belongs to R, tensor Cn. It is CC, CD. As before, I can write it as summation. I can write it in this way: H direct sum H tensor Cn direct sum direct sum G alpha tensor Tn when alpha is an element of R but not 0 and n is an element of Z. Right? We find delta from H to C, which maps C to 1, and H direct sum CC to 0, and consider any alpha belongs to H star as an element of H star by alpha C equals alpha D equals 0, right? Then, as an exercise, show that H is just L0, H tensor Tn is L and delta. You know what is the definition of L alpha. In fact, L has a weighted space decomposition with respect to H, and the weighted spaces are like this. And G alpha tensor Tn is just L alpha plus n delta. It means that L is direct sum of L alpha. L has a weighted space decomposition with respect to H. Support of L is 0 and delta and alpha plus it is R plus Z delta. Okay. And R hat, I mean support of L, is called the root system of F. Of course, with respect to H. As an exercise, show that if M is an L module having a weighted space decomposition, M equals M lambda, then for each lambda belonging to H star and gamma belongs to R hat, we have L gamma M lambda is a subset of M lambda plus gamma. It is very easy. It is just some computation. It is very easy because you know the definition of M lambda plus gamma. You know the definition of L lambda, you know the definition of L gamma, and you just should verify it. It's very easy. We can define bases, parabolic sets, and parabolic partitions for our hat. Okay? Parabolic sets, parabolic partitions, and bases can be defined as before. A parabolic set is a subset of our hat. When we say P is a parabolic subset of our hat, it means that P union minus P is just our hat, and it is closed in the sense that P intersection, P plus P intersection R hat is just a subset of P. You remember the definition, yeah? Okay. So we can define parabolic sets, parabolic partition, and bases. And now let's look at an example of a parabolic set. Assume zeta is a functional on a span of R over R, right? My field is C, and here I consider zeta as a functional on a span of R over R. If you are working with a general f of characteristic 0, instead of R, you can use Q, right? Okay. R hat set zeta to be all elements of R such that zeta alpha is 0 or greater than 0. It is clear that R hat is P zeta union P minus P zeta, right? Because if you have an element, zeta alpha is either greater than or equal 0 or less than or equal 0. So R hat is the union of P zeta union minus P zeta, and it is clear that P zeta plus P zeta intersection R hat is a subset of P zeta, right? Because if two elements satisfying these properties, for sure the summation also satisfying these properties, right? So using a functional, you can get a parabolic set. And it was very good if all the parabolic sets are of this form, but unfortunately it's not. Or maybe I shouldn't say unfortunately, because it's something that happened. Anyway, we can say about all parabolic partitions. Just look at this. Another example. Example, assume zeta is a functional on spanner R hat over R, and eta is a functional on spanner R hat not over R with R hat null within all alpha belongs to R hat such that zeta alpha is 0. Okay, look at the shape. We have R hat can be decomposed in this way. R hat plus, R hat null, and R hat minus. With R hat plus, I mean that all elements, for that one, zeta alpha is positive. This part is zeta alpha is negative, and this part is zeta alpha equals 0. So we have this decomposition, right? And then I consider eta to be a functional on the span of this part, right? Zeta eta to be R hat plus zeta union R hat null zeta R hat 0 plus zeta, R hat 0 null zeta eta. In fact, we have R hat has the composition like this. Right? What is the sound? It is from the room or it's outside?
Outside the room.
Okay.
Alarm for open security or
Yes, it was a fire alarm.
it sounds like
Should I check?
no, you can just close the door.
Okay. Okay, R hat has a decomposition like this, R hat plus, R hat null, and R hat minus. Forget about this part. And this part, using eta, we then have a decomposition for this part as well. A part plus, null, and minus, right? And we consider the first two parts. R hat null plus and null, right? And this is a set of R hats. to write null, it's not 0, it is null. It's different from 0. I try to put it somehow bigger to figure out it. Okay? Okay, so if we have a functional on S pan of R hat and then a functional on S pan of R hat null zeta, we get a parabolic set again, and it is easy to check that it is a parabolic set. But the interesting point is that all parabolic sets, all parabolic sets are in this group. If you have a parabolic set, you can find zeta and you can find eta such that that parabolic set is of this form. Okay? Let me write down the definition is two as well. And on these. That M is an L module having a weighted space decomposition with respect to H. We say M is a highest weight module M is a highest weight module with respect to a parabolic partition P of R hat if there exists lambda belonging to support of M and B belonging to M lambda such that M is ULB. In fact, M is generated by V and L gamma V is 0 for all gamma belongs to I minus 0. We call such a module highest weight module. And I told you about the construction of a high-speed module when we start with that specific G, but there is no difference, right? Exactly in the same way that I explained you for that example, you can start with a module for H, because when you have a partition for R hat, again, you have a decomposition for L, right? You can decompose L into L plus, L plus, H, and L minus. L plus is just direct sum of those L gamma, when gamma is an element of P minus 0, and L minus is those elements, direct sum L gamma, like when gamma is an element of minus pi 0, and then you can form a module, and then you get the quotient to get an irreducible one. It is the definition in general, but if you want to find an irreducible highest grade module, you can exactly follow the way that I explained you in the previous example. Right? But there is a question here. In the setting that I explained you, I always assume that we have a parabolic partition. And now the natural question is that what happens if instead of parabolic partition, we get a parabolic set, right? And we want to know what's happening when instead of parabolic partition, we use a parabolic set. Let's first look at the differences between the decomposition in the case that we have a parabolic partition and when we have a parabolic set. Suppose that P is a parabolic set of R hat. So, what was the difference between parabolic set and parabolic partition? The intersection of P and minus P is 0 in parabolic partition, but in parabolic set, we don't have this condition. Okay? We have P equals P minus P union intersection minus P union minus P set minus P. Okay, when we have a parabolic partition, this part is just one element set 0, right? Okay. Okay, and let's set L plus P to be direct sum of all L gamma, when gamma is an element of P minus P. And L minus P, the set of the direct sum of all L gamma, when gamma is an element of minus P, set minus P. Okay. And L null P to the direct sum of L gamma when gamma is an element of P intersection minus P. And if we have a parabolic partition, this is just H, right? If P is a parabolic partition, then L null P is H. And as H is finite dimensional abelian Lie algebra, we know what's the irreducible modules. And they are very easy because they comes from linear functionals, yeah? But in the case that we don't have a parabolic partition, it's very important that what is it, right? But anyway, suppose that I don't know what's the irreducible modules for L null P, but assume that we have an irreducible module. Assume omega is an irreducible L null P module. Okay, and I should mention that in general, 0 is an element of P intersection minus P. It implies that H is a subalgebra of L null P, right? So I assume omega is an irreducible L null P module. Having vector space decomposition with respect to H. Okay? Mu0 belongs to support of omega, and V0 as an element of omega mu0. You remember there is no difference between modules for a Lie superalgebra and modules for the universal enveloping algebra. So when I say omega is an irreducible module for this Lie superalgebra, it means that it is an irreducible module for the enveloping algebra. So if V0 is an element of this is a submodule of omega, right? But omega is irreducible. So we have just this, right? And you remember I gave you an example that if M is an L module, something like this, I told you prove this. L gamma, M lambda is subset of M lambda plus gamma. You remember? Right? And now, what happened for this? I can't exactly tell you what is the support of omega in some sense. Omega, this V0 is of weight mu0. So, omega is direct sum omega mu. Mu is an element of support of omega, or it's better to write H star here, and support of omega is a subset of mu 0 plus S span over Z of P intersection minus P. Right? If it's not clear for you, please tell me to explain it for you. If you need more explanation, please let me know. Look at this. L0, L null P is direct sum of L gamma. Gamma is an element of P intersection minus P. And L gamma V0 is a subset of omega mu 0 plus gamma. Right? And when you are this, you have a lot of these gammas consecutive, I mean gamma 1, and gamma 2, and gamma 3, and so on. And then you get omega mu 0 plus gamma 1, gamma 2, and so on. Right? And so support of omega is a subset of mu 0 plus S span of P intersection minus P. Okay, so now we can consider omega as a module over P. And P is just L plus P direct sum L null P. And you know how we can consider it as a module, because omega is a module for this part, and just define the module action to be 0 in this part. By L plus P omega to be 0. But P is a subalgebra of L, and so UV is a subalgebra of UL. So M, which is UL tensor product over UV, omega is a UL module, and so an M module. Right? So we start with a module for the null part, and then we get a module for F. But again, this M is not necessarily irreducible. We start with an irreducible module and would like to get an irreducible module. If there exists a maximal submodule, then we can make the quotient and get the irreducible one, right? Okay. What time is it? right. We have an L module here. And now we want to have a closer look at this module. Fix E alpha belongs to L alpha for all alpha belong to P minus P, and F alpha belongs to L minus alpha. Okay, and what we have, L is L plus P, direct sum L non-P, direct sum L minus P. And when we consider this one, if you fix a basis for this part and get a basis for this part and a basis for this part, you can get a basis for L. And when you have a basis for L, you have a basis for UL, right? And so you can get some information about this M as well, that we want to do it now. But look at this. M is UL, tensor omega over UB. And using a PBW theorem, as this part is a subalgebra, this part is a subalgebra, and this part is a subalgebra, as I showed you in the previous example, I can write it like this. L minus P, UL minus P, UL null P, UL plus P, tensor omega over UB. Because you remember, we had the basis element for UL according to the PBW theorem. There was some elements that you should choose an order. You should choose an order. We choose that order such that at first we put the elements of this part, then elements of this part, and then elements of this part. It is like this, right? And as we have a tensor product on UE, we know that this part with omega is 0. This part can be passed to this part, because if the tensor product is over UE, this part pass into this part, but the module action is 0, so we can omit this part. For this part, we just go back to omega, because omega is a module for this part, so it is just this one. It's panel X tensor B, when X is an element of UL minus P, and B is an element of omega. So, but using PBW theorem, Fi1 R1 up to Fit RT IT R1 RT greater than 0, and if one of Fi1 up to FIT is odd, or corresponding power 0 or 1. Basis for L minus P and each Fi is an element of L minus alpha. Okay, so M is S-panel Fi1 R1 FIC RT tensor V. I don't write these indices, it's like that one, and V is an element of omega. And we can identify one tensor V with V, so we have this S-panel Fi1 R1 FIC RT V, then is an element of omega. So what we have if V is an element of omega, we know omega has a weighted space decomposition, and we know exactly that subcourse of omega is a subset of mu 0 plus S10 over Z of P intersection minus P, right? So now, V is an element of mu omega for some omega. By the exercise that I told you about that, we get that Fi1 R1 FIC RTV is an element of M mu minus R1 alpha I1 minus RT alpha IT, right? So M equals direct sum M mu belongs to H star, and subcourse of M is a subset of subcourse omega plus S10 of P minus P over Z less than or equal 0. Because mu is an element of the subcourse of omega, and alpha I1 up to alpha IT are elements of, here we write here. Each Fi is an element of L minus alpha I and alpha I, because we have this element of this space, alpha I is an element of P minus P. So we have a vector space decomposition for M, and subcourse of M is a subset of subcourse on omega plus S10 P minus P over non-positive integers. Okay. And now we can prove that there is a unique maximum submodule N of M with N intersection omega to be 0. I told you that I identify one tensor V with V, so for V belongs to omega, so I can identify omega as a submodule as M. And because of that, I can talk about the intersection of two submodules, right? Okay. And so we can prove that there is a unique maximal submodule N of M with N intersection omega to be 0, and the proof is similar to the one that I proved it in the previous example. That one, the only difference was that here omega is not one-dimensional. It is in general, but let's look at the proof. Suppose that K is a submodule of M such that K intersection omega is 0. We claim that subforce of K intersection subforce omega is empty. In fact, as K is a submodule of M, and we prove that M has a weighted space decomposition with respect to H, each submodule also has a weighted space decomposition. So we have K is direct sum M lambda intersection K when lambda is an element of H star. But P is a parabolic set. So P equals P zeta eta for some functions. Okay. And so let's look at M lambda if lambda is an element of subforce omega. I told you that M lambda, it was a span of F I1, R1, F IT, RC, V, such that V is an element of omega mu for some mu belongs to subforce of omega, and the indices, I don't write them, are as before. and such that mu plus R1 alpha I1 minus RT alpha IT equals lambda. And what happens now? Okay. I suppose that lambda is an element of support omega, and I have this. Lambda and mu are elements of support omega. And support omega is a subset of mu0 plus S10 over Z of P intersection minus P. So there exists theta 1 and theta 2 belong to S10 of Z P minus P such that lambda is theta 1 plus mu0 and mu is theta 2 plus mu0. So what we have, mu minus R1 alpha I1 minus RT alpha IT equals lambda, but lambda is mu0 plus theta 1, and mu is mu0 plus theta 2. We can remove these mu's. So what we have theta 2 minus theta 1 is R1 alpha I1 plus RT alpha IT. And then theta 2 minus theta 1 is R1 alpha I1 plus RT alpha IT, and theta 2 minus theta 1. Theta 1 and theta 2 are elements of this part, so zeta is 0 over this one. So we get that this part also must be 0. And this part is 0. And it gives us that zeta R1 zeta alpha I1 plus RT zeta alpha IT is 0. But you know that these are greater than or equal 0, and these ones are yes, right? And what we get, then it means that these elements must be 0 because these ones are positive. So these elements must be 0, and so it means that theta 2 minus theta 1 is are elements of S panel R hat null zeta. But if we apply eta, it must be as it is 0, we get a contradiction because this part is 0, but that part is not 0. this part is 0, but the elements of that part are the elements of this part. We had P, eta, zeta, eta, which is R hat plus zeta, R hat plus zeta, eta, R hat null, null, zeta, eta. And now one part is an element of this, a summation of elements of this part, and other part is an element of some of this part. And it is a contradiction because they have an equality that eta on one part is 0 and eta on other part is not 0 because the elements are in this part, right? Okay. Then what we get? Right, so what we proved? Yeah, we just proved that in fact, we get a contradiction if all R1 up to RT is positive. So we get that R1 up to RT must be 0. So what we get that lambda equals mu. Yes, we get that m lambda is exactly omega. We get lambda equals mu and m lambda equals omega lambda. In fact, we get that if lambda is an element of support omega, we get that m lambda is exactly omega lambda. So what we have we had m equals direct sum m mu when mu is an element of H star. M lambda equals omega lambda if lambda is an element of support of omega. And K lambda equals M lambda intersection K. And we have K intersection omega is 0. So all of this together give us K lambda, which is K intersection M lambda, is 0 if lambda is an element of support omega. Right? Now what we have, K is direct sum K lambda. Lambda belongs to support M. Lambda is an element of H star. And we get that if lambda is an element of support omega, then K intersection M lambda, which is K lambda, is 0. So it is direct sum of K lambda when lambda is an element of support M, but not support omega. So if we set N to be the summation of all K, when K is a submodule of M, but K intersection omega is 0, then we get that M lambda equals 0 if lambda is not an element of, if lambda is an element of support omega. So it shows that the summation of all submodules like this is again a proper submodule. So we have a module which is the summation of all submodules which intersect omega trivially, and this n is proper, and I showed you that n lambda is 0 when lambda is an element of support omega, so n intersection omega is also 0. So n is a maximal submodule intersecting omega trivially, and for sure it is the unique one because I made the summation of all such modules, right? So I can make the quotient, and as n is maximal, the quotient is irreducible. Now, m over n is an irreducible L module. So, what I did, I start with a parabolic set. I had a decomposition for L plus P, direct sum L null P, direct sum L minus P. I get an irreducible L null P module. Then I get M as UL sensor UB omega. This M is a weight module, and then I can form this module. This is an irreducible module, and then the only problem here is that we don't know the irreducible modules of this part, right? And the question that people try to find the solution is that if we have a module for the superalgebra L, right? If we have a module, if there exists omega and a parabolic set such that that irreducible modules can construct it in this form or not. I start with omega and construct an irreducible module. And the question is the vice versa. If we have a module, if we can find a parabolic set and omega such that that irreducible module is of this form. And next section, in the next session, I will tell you a little bit about this, right? Thank you.